Let f of xyz equal xy squared times the inverse tangent of z. Find the directional derivative in the direction of v, which is 1, 1, 1, at the point 2, 1, 1. I'm going to ask you to pause the video and work on this in just a minute, but first, notice that the vector is given to be v and it's 1, 1, 1. I want you to think about that because everything we've been looking at so far is the directional derivative in the direction of u. So what's up with this being v? Think about that, crank through this, and then come back when you're done. Well, here we are. We see that the magnitude of v is square root of 3, and so u, the unit vector, is 1 over the square root of 3, 1 over the square root of 3, 1 over the square root of 3. So we note that v was not given to be a unit vector. We have to start with a unit vector. That aside, del f of xyz is going to be the partial of f with respect to x. So that's going to be y squared times the inverse tangent of z. Then the partial with respect to y, so 2xy times the inverse tangent of z. And then the partial with respect to z. Differentiating the inverse tangent function is going to give me a 1 plus z squared in the denominator, and the numerator is, of course, the constant with respect to z, xy squared. Evaluating those components at 2, 1, 1, we get the vector pi over 4, pi 1, that's del f. The dot product then, which is going to give the directional derivative of f in the direction of u at the point 2, 1, 1. I know, I wish there was a quicker way to say that. Is going to be the dot product pi over 4, pi 1 with 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. After getting common denominators and collecting like terms, we get 5 pi plus 4 all over 4 times the square root of 3. Let's explore this gradient a little bit more. I'll note that the directional derivative of f in the direction of u, which is given by del f dot u as a dot product, can also be expressed as the magnitude of del f times the magnitude of u times the cosine of theta, using the physics definition of the dot product, where theta is the angle between del f and u. But since u is a unit vector, the magnitude is 1. And so that means that the directional derivative of f in the direction of u is the magnitude of del f times the cosine of theta. This is going to have a maximum value depending on the angle of that theta represents, right? The maximum value of the cosine of theta occurs when theta is equal to 0, which means that del f would be parallel to u. And the maximum value of the directional derivative is the magnitude of del f. In order to understand this, we're going to look at a diagram. Suppose we have a surface in R3. The surface is given by z equals f of x, y. So we're talking about a function of two variables, x and y. With that being the case, that means that del f has two components, fx and fy. I'm going to give some contour lines to the surface because I think it'll help a little bit. And I just noticed I didn't close the parentheses around this little parenthetical del f is equal to the vector fx, fy. Was that bothering any of you? It would have bothered me. It bothered me so much I fixed it. Anyway, folks, suppose we have a point P on the surface and it's got a shadow in the xy plane. And if you were standing on the surface at the point P, you can look and see which way is the steepest, what direction would make you go the steepest, and what direction would be the steepest in the other way. In other words, which way would water flow, right? I think looking at this, that water would probably flow right down here off of the surface, right? And the backside of that, the opposite direction, looks like if you were hiking, that's not the way you'd want to go, unless you just wanted the challenge, right? Associated with these two directions on the surface are vectors in the xy plane. And it looks like maybe these vectors might look like, yeah, I'm going to go right there. and then the negative of that vector here. This vector in the xy plane is the direction of maximum increase. And the opposite, the negative of that vector, where water would run down, is the direction of maximum decrease. So what do these maximum increase and maximum decrease have to do with anything that we're talking about? It's this. The gradient vector itself, this two-dimensional vector, gives us the direction of maximum increase. In other words, as a two-dimensional vector, it basically tells you, if you're standing at the point P, which way to look, north, south, east, west, whatever, to find the direction of maximum increase. That's associated with a vector in the xy plane. And so even though we're looking at a surface in 3 dimensions, to know which way to look, you really just need 2 components. And then to know what the actual slope is in that direction, we find the magnitude of the gradient vector. All right, so we have here the maximum value is of the directional derivative in the direction of u is del f. And we can wrap this up by saying del f points in the direction of the maximum change of f at a point P.